Alright, as promised, let's talk about the test first. AP exam. Yeah, it did. Here's the breakdown. What I want to point out first is you'll notice that the mass majority of this test is differentiation. Different categories of it, but differentiation for sure. So the basic differentiation, like being able to take a basic derivative, 10 to 12%. Using composites or inverses, using things like the chain rule, 9 to 13%. And then your applications, so things like the first and second derivative tests, tangent lines, secant lines, another 20 to 25%. So like, it's big. Limits of continuity, 10%. Much smaller, but a couple questions every year. Integration comes to about between 27 and 35%. And differential equations, which is what we'll talk about the week before. Again, it's just a short little section there.
Corey Tuttle, Brandon Wakely, and Seth Turner to the office.
Let's talk about the test itself. So,
I saw you when I was pulling it out this screen.
the test has 4 parts to it. First part number 1. 30 multiple choice questions. You got 30 questions in 60 minutes. And these are the ones that have no calculator allowed.
So I'm a district champion in academic game.
Nice.
You know, she'll drop out, so now we're going to state.
Nice.
Mr. Holt said not to
Never
say
hear.
that part.
Okay. The calculated portion has 15 questions. And takes about 45 minutes.
Ooh.
Now, after the multiple choice questions, there are 3 response questions. Again, there'll be calculator and non-calculator. Calculated portion, there are 2 free response questions. Just 2. They will have multiple parts, unlike the ones you've had for our tests. And they take about 30 minutes. The non-calculated portion. There are 4 of them.
Gee,
And they gave you an hour.
that's all.
So,
You're telling me most people in the United States don't pass this test on average?
yeah.
Have you taken an AP test before?
No.
You'll understand why.
Now, some general test taking strategies that I pulled from the ACT that I think apply very well to the AP test. First things, prioritize questions. Don't start with question 1, then do question 2, then do question 3. They are not written in any order typically, and so you want to bounce around and get as many of them correct as possible. If you just skip the first 5 questions and go to question 6, because question 6 is a better one for you to do, it's better to do that than to spend half an hour trying to answer those 5 and then rush through the rest trying to finish them in the remaining 60 minutes. It is always far better to get questions right than to not answer them. So, get used to the idea that you shouldn't perform a test linearly. You should evaluate a question and ask yourself, is a question I think I can reasonably answer in 2 minutes? If it is not, move on. Take a shot, move. It is worth the time. Now, other things both in the AP exam. We will discuss, when we talk about the differentiation stuff, some things your calculator can use. On those days, whatever calculator you are using for the AP exam, I want it in your hand on those days. I'll showcase some of the tricks and things you can use, like the graphing tools. We talk about some of them in class. We'll spend a day just looking at some of the useful things and how you can learn from a question how to use them properly. But again, in general, the calculator questions are ones that specifically require a calculator. Like, they're meant that you need a calculator for them. The last thing is like, okay, do you sign at 1.6? Like, it's one you can't do without. On the other hand, you have some that you say don't require calculator at all, that's not calculator portion entirely. So, it's your AP exam. Now, over the next week, We're going to focus on the last thing that we haven't talked about, which is the application of integration. And over the remaining 2 weeks we have until our test, we will hit each one of these categories and go through questions each day, going through how the different questions are asked, tips and tricks you can learn, as well as reviewing the big stuff that comes every single year. So that's for the next couple weeks. That's what we're going to do.
So far, we're not taking the AP test and we have to take that test in class. Is it going to be for a grade or participation?
It will be for a grade. You're not getting any speed exam has to be for a grade. It's your time. So for that test specifically, the big thing about it will be cumulative. It will be the whole year. It won't be just the last stuff we talked about. So guaranteed to be at least one question on that final that deals with limits and continuity. One question that deals at least with differentiation of the basics, composites, applications, as well as analytical applications. With a question on integration, with a question on differential equations.
This was really good to learn. We learned a lot this year, but it was all
they fit into very big categories, right? Like all of integration we learned about in a month and a half, and that's 2 sections of this thing. And that's a lot of stuff we talked about. As far as stuff you need to know for the AP exam specifically, every formula on that cheat sheet would be good to know. Every single one. Other than that, know your calculator well. And the last thing I'm going to tell you is what we're going to work on after we finish this last section on integrations, this little application portion. After you finish that portion, the only other thing I can tell you about the AP exam that's really good to know is how to decide what kind of problem it is. Is it a derivative problem? Is it an integration problem? Is it something else? Because the derivative problems all act very similar. The integration problems all act very similar. The ones that are other fit into a couple of very key categories. They're either limit questions or differential equation questions. And so once you figure out what kind of question it is, it can lead you down the right path to how to solve it. But if you can't figure out that first basic component of which of these things am I supposed to be doing, this test becomes very, very hard. So, any questions before I start talking about the last piece, applications? Okay. Let's talk application. We're going to talk about 2 applications this week. These are the main applications of integration. Area problems and volume problems. There are further applications. They're discussed in Calc 3. Things like surface area, resistance along the wing. If you want to go into most engineering cases, you'll use Calc 3 the most because applications of integration and applications of differentiation. And so you have to know the basics before you can learn those advanced things. Let's get started. So, applications. In general, applications are going to fit into 2 broad categories for integration. They're going to be whether you're talking about an area problem of some kind or a volume problem of some kind. And so things that can pop out to make this look very simple is your units, what the question asks you about. You guys have taken math for a long time now. The units for area are always something squared. Units for volume are always something cubed. If the problem mentions one of those things, that can lead you in the direction of which one you're supposed to be working with. So, the applications. Like I said, there are 2 main ones. Area problems, which we've discussed, the most basic kind. There's a second kind that has some really neat stuff to it. Like really, really cool stuff. And then volume. So, over the next couple days, we're going to be looking at these 2 categories, and specifically at 2 things in each category. The area. We're going to look at the basic ones again, just as a reminder to see how they fit together. And before we leave today, we're going to look at the advanced ones, which looks at between 2 curves. So obviously, as we discussed in class, there are area problems, but these are really basic ones, always involving axes and how they fit together. The between 2 curves is the most common application. It is more advanced, but once you understand how it fits with the other ones, it actually is very simple. Now the volume ones, we'll talk about 2 main techniques, the disc technique and the washer technique. Both these very similar. Once you understand how they kind of fit together, it's actually a pretty straightforward problem to work with. So let's go with the first thing, area problems. We've done integration of area before. The integration of the area problems are when we have those bounded integrals, where we have a lower value and upper value describing an actual integral. So let's look at some of those first and discuss how they fit together. So what we're going to do, we're going to find the area between three distinct things. A curve, something like y equals x squared plus 2x plus 1. And then we have to describe the boundaries around this piece. So I might say something like, hey, on the left-hand side, when the x value equals 0. On the right-hand side, when the x value equals 3. And then typically we want to declare an axis like the x-axis. All this information does is it leads us to the fact that this is supposed to be an integration problem. If you see the term area, that screams integration. Or it screams geometry, one of the two. You've had geometry before. If it looks like a geometry problem, do geometry. We saw in class when we were talking about some of the area problems, it is much easier to do them with geometry sometimes than with calculus. So do them with geometry if it's a geometry shape. If it's a half circle, use a half circle formula. If it's a triangle, use a triangle formula. Don't integrate that. But if it's one like this, if I graph this function, it is not a function that's easy to determine the area of by standard techniques. Example, in this case, the graph looks something like this. And we were asked to find the area between 0 and 3 and the x-axis. So that red area there. Now, that red angle is close to a trapezoid, but not quite. We could do things that we talked about back in January, like doing like a Riemann sum, where you break this into tiny rectangles. No. Integration problem. You see area in a problem that screams integration. So, I look at this problem, and I integrate this thing. Now, to define my integral, I need to know a couple things. Number one, what the equation of integrating is. Well, that's the first thing. It goes inside x squared plus 2x plus 1. Second thing, I need to know the boundaries. Where it's going to start, where it's going to end. The lower boundary needs to go, of course, from the bottom. So the left-hand number goes on bottom, 0. The right-hand number goes on top, 3. And then the fact that the x-axis indicates that we are doing this with respect to x. So that means my final thing is that this is a integration with respect to x. Now, as a reminder, on these kind of integration problems, the fact that they're bounded, the way to do them is you integrate the entire function, then plug in the top number, plug in the bottom number, and subtract them. So, to define my solution, I take this function and first integrate it, and then I will plug in 3 and 0. So let's start with the integral. To do the integral, remember I do this in separate pieces, so let's think about each integral. Integral of x squared. 1/3 x cubed. Integral of 2x. X squared. We add 1 to the power, divide by the new power, it becomes just x squared. And then plus 1, x. Now, to determine the area of this function, I first integrate. Congratulations, that's Jeff. And then I evaluate. So what I do is I take these two boundaries, 3 and 0, and I plug each one of them in. So I plug in 3, 1/3 times 3 cubed plus 3 squared plus 3 minus 1/3 0 cubed plus 3, no, 0 squared plus 0. So it'll be 21. That means that the area between 0, 3, the x-axis, and this function is 21. Seems a lot bigger than it looks, but it's true. It's 21 square inches, 21 square units. So these are your basic integration problems. They get more advanced by using more advanced functions, but they're still very simple in terms of what they use them for. You find the area, you have to have boundaries around them. Very straightforward process. Now, the secondary component is an application. So, as you might imagine, this shape, as neat and interesting as that shape might be, most things in the world that you're going to be manufacturing are not going to take on such a nice round shape. Even in geometry, I know that whenever I took geometry, I was really annoyed because it's like, here's these area formulas. I'm like, yeah, but most things don't fit these shapes. Like, trapezoids aren't that common in the real world. Circles aren't that common. You know, they're formulated, they're molded into something else usually, especially in nature. And so, there's a secondary test. Integrating between two curves. Now, this I'm going to use Desmos to help because it's much easier if you have a picture of this function. So let's do that. Here you go, Desmos. Give me here. So that was my first curve. X squared plus x plus 1. Let's look at the difference between two curves. Here we go. Yay. So first of all, you can tell you're going to be using this technique if you have two curves given to you. That is usually a prime indication that you're going to be using this advanced technique. They'll say, hey, here are two equations, find the area between them. On the previous problem, it usually mentions an axis as opposed to a secondary curve. That is how you can tell between the basic and the advanced. If it says an axis, it's the basic. If it says two curves, it's the advanced. So what we're going to do, we're going to determine the area between two functions. In this case, the first function is going to be just a basic function x squared. The second function is going to be the area between this and sine of x. As you can see, there is a distinct area set up in between these two. This area is the one we are going to find. Right there. Again, you can usually tell these are meant to be the advanced kind if they give you two equations to work with. If they say, hey, here's x squared, here's sine of x, integrate between them, that's an indication you're going to be using the advanced integration technique. If instead it says, hey, here's one equation, find the area between this and the axes, we use the other two. Now, the major difference between these two is actually a pretty simple operation. We have the ability to find the area between anything and a axis. That's what the basic integration rule says. In order to do this technique, we need to know two things. Number one, you have to know when and where these functions cross. Because unlike with the previous one, the boundaries are not defined by arbitrary numbers, they're defined in the picture. This value right here comes from the formula. This value right here comes from the formula. And so I have to be able to find those values in order to do this. Now, let's see, there's a graphing calculator to help out a little hot with this. Because it should be able to tell you exactly where those values are. If it's a non-calculated problem, you're probably going to have to do some algebra to see where these two equations are the same, or we call it in math, equal. The easiest way to do that is step equal and solve. So step one, in order to do these kinds of problems, you must figure out what are called intersection points. You have to know where the intersection points are, otherwise you cannot do this. So in this case, for this problem, to determine this integral, I have a single intersection point at 0. And I have a secondary intersection point up here. Now, where that one is located, a little bit harder to do. A calculator is a great assistant to this kind of one. Michael, does that have a deal with right now? Find that boundary for me? Yeah. Now, so this is a place where in this case x squared is supposed to be equal to sine of x. So that's the equation I would have to solve. Now this is not one that would typically be solved by hand because you're mixing algebra integration with trigonometric function. What you see that these this is with is an algebra problem. So, you know where it is?
Yep.
Where is that?
0.877 on the X.
So, 0.877 is around the square root of 3. No, square root of 3 over 2. So there you go. Cool. Yay! Make use of radians.
Yeah.
Okay. For your entire AP exam, make sure your calculator never leaves radians. Everything is done in radians like we've done nearly for this entire year already. Everything in radians. Okay. So this gives you my two boundaries, a 0 and a 0.877. Well, now we have a way to integrate this thing. So we integrate between 0 and 0.877. But what goes inside? Now, the rule is very simple. First of all, you have to find the intersection points. That is step 1. Step 2, after you have the intersection points, you have to determine the order. Because what's going to happen is we are going to do a basic subtraction problem. The reason being, if you look at the picture, it makes a lot of sense. We can determine the area between the upper curve and the axes and the lower curve and the axes and use that to determine the actual area itself. But to do so, we need to know two things. The top function versus the bottom function. What you will do, you would integrate top function minus bottom function. And lastly, since we have x values that we have chosen, we're going to do it with respect to x. Which also leads to the question of what if we don't want to do it with respect to x? We can also do it differently. Now, the way I was always taught was called the teardrop test. If you're crying on this curve, this is a hard math problem. Which function do you hit first? That's the top. Which function do you hit second? That's the bottom. When it comes to changing it to a different functional value, this is a little different, but for now, let's stick with just x's. So, what we have to do is we have to determine the intersection points, step 1. We did that, thank you, Michael. And then step 2, we have to determine the order. Which one is on top, which one is on bottom. In the picture, that's easy to do, isn't it? Without the picture, it's annoying. What do I recommend? Take the picture. Alternatively, if you're not sure, plug in a number in between them and see which one's higher. Plug in a half into these two functions and see which one's higher. Because again, we have to know which one's on top. So if I plug in a half and the sine function is bigger, then that's top. Plug in a half and the x squared function is bigger, then that's going to be the top. Again, so the intersection points and the order. Once we have these two things, now we just integrate like we've been doing all semester. So this actual function, here's how we do the problem. I'm not going to erase this. I apologize. Hope you got those two numbers in your head, 0 and 0.877. Here's how I solve the problem. Integral between the two intersection points of 0 and 0.877. I take the top function, which my top function is the sine function, minus the bottom function. My bottom function is x squared. And since I'm doing everything in terms of x, it is dx. And now I integrate. So to find the area between these two curves, I do an integral between 0 and 0.877 of sine of x minus x squared dx. Again, the top one in blue, the bottom one in red. Subtract them. So, what's that area? Alright, calculator's your friend here. Let's do it. So, integral of sine, negative cosine, minus x squared.
Negative 1/3 x cubed.
And we're evaluating between 0 and 0.877. So I plug in the top one first, and I plug in the bottom one, and start solving. I'm going to show my work here. So I would do first negative cosine of 0.877 minus 1/3 0.877 cubed. That is the first one. Then I would subtract from that the second one, plugging in 0. So I get negative cosine of x, so it'd be, in parentheses, negative cosine of 0, minus 1/3, 0 cubed. I'm running out of room, guys. Calculator be your friend. Next one won't have a calculator at all. Okay, what did we get? Was that good? No, that's good. Don't be afraid. You're only by a little. .135. This area is equal to units squared, whatever it happens to be. That's it. You notice it's a pretty straightforward process, but it's considered advanced because it's not just a basic integration. You have to put the integral together yourself. Again, those two parts, very key. I have to first determine where I'm crossing, and once I determine where I'm crossing, I then determine what my actual functions go in the order themselves. So let's try one where I don't do the graph. This is actually your first homework problem. So, take a look. Your first homework problem says, determine the definite integral that gives the area of the region. So it's not actually asking you to solve anything, but we're going to solve it. So let's talk about it. It says, we have two functions, y1 and y2. y1's function is x squared minus 4x plus 3. Second function is negative x squared plus 2x plus 3. We're going to find the area in between these two. Okay. To do so, remember our two steps. Step 1, we have to find the intersection points. Unfortunately, I did not give you a picture, and this is not a calculator problem. So, set them equal to one another, and solve. Let's do it. If I want to find the intersection points, the easiest and best way is to take y1 equals y2 and solve. So what do? y1 is x squared minus 4x plus 3. Again, if I have a graphing calculator, I'm not doing these steps. I'm plugging them into the graphing calculator, like, there it is, right there. Look, right there, I see it. Come on. Equals negative x squared plus 2x plus 3. All right, algebra 1 brains, turn them on. 2x squared minus 6x equals what? 0. Now what do we do? Okay. An x? I heard 2x. I like a 2x better. And what's it behind? So what are my solutions?
0 and 3.
So, my two intersection points. Now I can start my integral. My two intersection points are at 0 and 3. Again, fundamental theorem of arithmetic. 0 is one solution, 3 is the other. Okay? But before I can take my next step, I now have to decide step 2. Step 2, order. Remember, the formula is top, in quotations, minus bottom. These can change. What we're really concerned about is in between 0 and 3, which of these is the top value, which of these is the bottom value. You can also use other things like how the function is structured. If you know how x squared acts, and that may indicate how this function is going to look at this specific interval of time. So, my best solution, plug in something in between. If you're forced to do it by hand with no calculator, plug in something in between. So in this case, I'm going to plug in the number 1. Why 1? It's easy. Could I choose a dead center, 1.5? Yes. Does that mean I'm now plugging in a fraction, having to do the math for the fraction? Yeah. Do I want to do that? No. Plug in an easy number that's in between. If there's not an easy number in between, find something close to the easiest number. Okay, so I plug in 1. So 1 squared minus 4 times 1 plus 3. 1 squared is 1 minus 4 times 1 is negative 4. 1 minus 4, that'd be negative 3 plus 3. So 1 gives me 0. So it gives you 6. So then which was my top function? y2. So in this case, I'm going to integrate y2 minus y1 with respect to x. What this will do is it'll find the area in between these two curves because I have set up the intersections between them, 0 and 3. I have put them in the order, the top equation minus the bottom equation, and now this becomes a basic integration problem. Let's do it. Is equals the integral between 0 and 3 of y2, so that's negative x squared plus 2x plus 3, minus y1, x squared minus 4x plus 3. With respect to x, you'll notice that I put them in parentheses because I want to make sure to distribute that negative correctly. Most common mistakes are algebraic mistakes in this class. Forgetting a negative, distributing wrong, that kind of stuff happens a lot. So now I set this thing up. This becomes the integral. You'll notice that I'm simplifying now before integrating. If possible, simplify before you integrate. We'll save you a lot of headaches later. So let's simplify this as much as I can. So this becomes negative x squared minus x squared. That'd be negative 2x squared. Positive 2x, negative, double negative, make that positive 4x for plus 6x. And then the zeros, dx. What you might notice is those two are really similar. They should be. Okay? It depends on the order which one will be the positive and the negative, but they should be similar. So notice that this complicated problem reduces to a simpler standard integration problem. Speaking of which, let's actually solve this thing. So we integrate negative 2x squared plus 6x with respect to x. All right, so I go 0 to 3. All right, let's integrate. Negative 2x squared, how do we integrate that? Negative 2/3 x cubed.
Plus 3x squared.
Plus 3x squared. Evaluate between 0 and 3. All right? As a reminder, when doing a problem like this, I take the top value and plug it in first. So I do negative 2/3 of 3 cubed plus 3 squared, minus negative 2/3 of 0 cubed plus 3, 0 squared. And we simplify. So,
Third hour drama will be meeting in the pack. Third hour drama will be meeting in the pack.
so the answer is 9. Nice thing. Now, when you look at the picture, it's much easier to see that, yes, this is the top one, yes, this is the bottom one, these are definitely the two boundaries. It's much easier when you have the picture. Without a graphic calculator, you have to graph it by hand or do algebra. Now, I respect every student who tells me that they don't like to graph. I get it, I didn't like it either when I was younger. I understand. If you're good at graphing, you can sometimes graph these faster than you could do them by hand. Algebraically. Just know that. It's a thing. It's kind of hard to fix now, but you can be like a little time travel device and yell at your first grade or freshman self and be like, learn to graph better. If you're gonna do that, like stop Hitler and stuff too. Don't be selfish kids.
Butterfly effect, don't stop it. But
Never stop Hitler. Wow.
as crappy as that sounds, butterfly effect, you don't know what could happen.
America. Alright.
Freaking Hitler Stalin could be taken over, you don't know. Like you kill Hitler,
Take this left.
more
Okay.
Hitler comes up.
As you can see, this is pretty straightforward. The cool thing about this one is that there's a neat consequence because you can do it with either variable. Now, here's the thing. We'll discuss this more later this week when we continue the discussion of the volume problems. In general, you can do it with either variable as long as you turn everything into the other variable. Meaning you have to get x by itself instead. Let's look at one where it's a function where it's in terms of y rather than in terms of x. This is a relatively simple one. This is, I believe, also a homework problem. In this case, my two functions are f of x, no, f of y is y squared, g of y is y plus 2. Could this problem be done in terms of x? Yes. What you'd have to do is solve for y. Essentially kind of the opposite of what you've done in a lot of algebra classes. What you would do is you would turn this into x equals y squared, and you'd have to work to get y by itself, so take a square root of both sides. On this one, you have to do the same thing. You'd have x equals y plus 2. And again, you have to get y by itself because, again, the techniques work if the variable is isolated. That's why so much of algebra is about getting a variable by itself. Now, we're going to pretend that we are so smart, like, nah, we got this. No need for any of that silly x stuff. We're going to do this all with respect to y. The rules do not change. Step 1, intersection points. Where do these two things cross? We'll find out, same way we did it on the previous problem. Set the two things equal to each other. So in this case, I'm going to do f of y equals g of y and solve. So, to find out whether they equal to 0, I just do y squared equals y plus 2. Okay, algebra hats on. Y squared equals y plus 2. How do I get a solution for y? Square rooting will make it worse, unfortunately, because my goal is to get all the y's together. I'd subtract both pieces.
Oh, I see. And then it becomes quadratic.
Yep, and then it becomes quadratic.
I was just gonna finish this one. Okay.
Quadratics are really useful here. Okay, we can factor it. Quadratic formula, anything that works here. Anything that would have worked with x would work with y as well. So, factor. How does this break down? Y minus 2, y plus 1. So what are my two solutions? So my 2 and negative 1, these will become my boundaries. So it's become the integral from negative 1 to 2 of my function. All right. So again, now step 2 comes into play where I have to decide what order do I want. Step 2. Say again?
Can you just plug in 0?
Yes, so I plug in a value in between these two. She says 0. Great option. So g of y is definitely larger because I plug in 0 there. I get 2, I plug in 0 here, I get 0. 2 is bigger than 0, so g of y has to come first. So I do g of y minus f of y dy. Everything we've done so far has been with respect to y, so we should stay in respect to y when we do the integration. So the nice thing is, again, everything is in terms of y, so we integrate the exact same way as if it was in terms of x. It's just now with a y involved. Integral from negative 1 to 2 of y plus 2 minus y squared dy. Simplify what I can, and then we integrate. If I simplify this, it doesn't get much better. But again, you'll notice that the equation we found earlier is similar to the one we find here. The order is kind of what matters. This becomes negative y squared plus y plus 2 dy. Nope, can't do that. I haven't integrated yet.
Oh, yeah.
I have to integrate. But you're on the right track. Let's do it. Integrate this thing. And then you plug in 2 and negative 1. You see where this is going. In a second, I'm going to actually graph these two and show what this one looks like. It's not much different. Before I do so, let's go ahead and find our solution. So again, if you want to do it in terms of y, just make sure every piece is in terms of y. Both equations and the boundaries. The boundaries have to be in terms of y as well. Here we go. So I plug in 2, so negative 1/3, 2 cubed, plus 1/2, 2 squared, plus 2 times 2, minus negative 1/3, negative 1 cubed, plus 1/2, negative 1 squared, plus 2 times negative 1. Now we get some fun algebra. Minus negative, no, cubed will make that negative still.
Well, yeah, but then you put them together. Oh,
Positive.
they're negative.
So this becomes 1/3. Distribute the negative. Negative 1 squared is positive 1. 1/2 times positive 1 would be positive 1/2, but negative of that would make this negative 1/2. 2 times negative 1 would be negative 2, but the negative would make that positive 2. So this becomes negative 9/3 plus 3/2 plus 6. That's negative 3. This becomes 3/2 plus 3, or 4.5. Love this. But in the moments we have left, let's graph this function and talk about what it looks like. Sorry, JJ. That's good. I did a bunch of crazy simple math at the end. Okay, so these are ones where you have a calculator. It actually makes it really difficult because the calculators are designed to only work in terms of y, not in terms of x. So f of y, g of y do not like to work in a lot of TIs, especially. If you have one of the fancy graphing Casios, those actually do have a way to graph in terms of y fairly easily. You just got to go to the menu and figure it out. But if you want to graph this with a graphing calculator like my TI-84, it's very difficult. You have to do it almost entirely with respect to x every single time. But let's look at the two using Desmos. So my two equations in Desmos were x equals y squared and x equals y plus 2. So the area we just found was that area, which I want to point out something special about this area. First of all, in the y values, the top y value is 2. The bottom y value is -1. But where it gets annoying and why it's going to do it in terms of why for this particular problem is, what's the top equation and what's the bottom equation gets muddy if you do it in terms of x. Look over here. If I imagine a teardrop rolling down my paper, because I'm so sad about this problem, over here, the green equation is on top, the purple equation is on bottom. Makes sense, right? But if I move this to the left, suddenly the same equation is on both top and bottom. So how do I do that? If I go over here, the top equation is green, the bottom equation is also green. How do I do that? The answer is I don't. I do it in terms of the y's. Now in terms of the y's, you remember that we put the y plus 2 as the top. It's better to think of it not as the top, but as the farthest away. Because now what happens is, if I'm thinking in terms of the y, I gotta crunch the y-axis. So I draw my teardrop going this way. And yeah, I cross the purple one first, the green one second. And I do that everywhere in this boundary. Purple one first, green one second. Purple one first, green one second. Everywhere I go, I touch the purple one first, the green one second. So while the book says to do top minus bottom, I prefer to think outer minus inner. I have to remember that with x, that means I'm going top to bottom. With y, that means from right to left. This is one of the primary applications of integration. And you notice this takes it and allows us to do a lot more complicated equations, a lot more complicated pictures. Because this picture, look at that original picture, man. It's beautiful. This space in here, this could be the shape of an aircraft foil. This could be the shape of a logo you're doing for graphics design class. You have to determine the area specifically so you can print and manufacture it and tell the pricing of it. Like, we have a huge amount of more things we can do, and the creativity of how we can put equations together is all that limits us. Questions on today's material?
Also, are we ready to the office? And Jason met tax for checkout.
Okay, I will post your homework assignment here in a few minutes, hopefully by the end of the day. It will be 3 through 51 every other odd. Starts at number 3. It starts on number 3. 3 through 51. I'll post all in the classroom. It is just practicing these techniques we talked about in here. Test, please.
Yeah. You know what? I'm just gonna go with what you said because I really okay. I don't have the great for it. My answer for 5 is A. A? That's probably wrong, isn't it? Yeah, I don't know.
I'll be honest, I slept in bed with this.
Yeah, okay. It was. Oh, I don't know if you probably told me email. I just didn't know because it was an undefined portion, like of.
Yeah.
So I didn't know how that would work with a derivative still.
Remember what the actual equation was?
-3.
Both are done.
I got it. Actually, it's -2 over 3 x plus 1 x minus 1.
X minus 1?
Yep.
That?
Yeah. That was the derivative of it. And then the original was natural log of x plus 1 over x minus 1.
Natural log. X plus 1 over?
X minus 1. Yeah, so originally I did do the shortcut, cube root of that, sorry. So just 1/3 natural log of that, so. Originally I did do that shortcut, but then I was like, oh, I must have gotten it wrong because this doesn't make sense.
This is all cubed, right?
To the cube root.
Yeah.
Yep. Yeah, so.
Wasn't the boundary
Haley
between 1
Morris,
and
Jack Cornell, and Harley Ray to the office.
Boundary. It was just a free response. It was just find the derivative and find the point. The confusion I had was whenever I got the derivative and I graphed it and I saw that there was still a slope to the undefined portion of the graph. I just didn't know how that made any sense.
Okay, there we go. This one, right?
So it didn't really affect the problem itself. Like I could still get to the same answer and everything with this, but I was just wondering, what is this portion up here?
What's the slope at that?
What's going on,
But
dude?
it's undefined, isn't 3 here? It's an asymptote.
Oh, I'm still cold.
And then there was a boundary somewhere where it limited that actually.
Don't you get absolute value whenever you do the natural logs derivative?
This hurts. Oh. That much I can.
Is it not?
It was just 1 over a times the derivative of that, or times the
So-
the inside.
Casey got a different solution for her answer.
Jack Cornell to the office. Jason
She
Metcalf,
got-
is that down?
Hopefully we go away.
Oh, it was 3 times
No,
3, so she just boiled it down.
So rough carrying 2 on that down.
Okay, that looks, yeah.
Okay.
I'm gonna leave for the next 3 days.
Yeah, I also looked it up just on a calculator to see what.
Yeah, it should be undefined, so it should have an absolute value in there. Because this middle portion, so what happens is, in the original function, this middle portion does not exist because you get it with negative solutions, right? And so what happens is, the derivative then shouldn't exist in between the two either. The original function doesn't exist. So if I was looking at this problem, I'd say, okay, then that means that this piece doesn't exist.
So straight up, just
I'd say this is the derivative for x not equal to.
so you would just ignore this piece entirely and just say, well, it doesn't exist.
Yeah.
Okay. I was just wondering because I thought doing derivative.
Yeah, you put a boundary on it.
Huh.
Like, yeah, ignore everything else.
I did not put a boundary.
Which I didn't tell you guys to. We didn't talk about that in class. What you have is the derivative. We just couldn't do it at 0 because it doesn't exist at 0.
I did the rest of the boundary. Like,
So this is the slope of the imaginary line.
Jason Metcalf, you're needed in the office.
So
Is that down?
there are
Jason
values and
Metcalf,
negatives, they're just
you're needed in
imaginary
the
values.
office. Is that down?
And so it can have a slope.
I guess I'm
So it would be a slope in the imaginary.
That's what we got.
That's okay.
yeah, but I thought it was
I'm
because
saying
of this right here of it being over 0, that makes it undefined and not just.
if you modify 3 months, it'd be like 200.
Well, this piece specifically interacting with the top piece. So what happens is if I plug in
I don't think you're
1, the bottom becomes undefined, right?
Yeah.
If I plug in 0.9, the bottom becomes negative, the top is positive. Positive divided by negative is a negative number, and the absolute value, or the natural log of the negative number does not exist in these values. When I get over here to -1, the top becomes 0, which is allowed. You can have a natural log of 0. And then what happens is, as we get further and further in,
Oh, I see.
both the top and the bottom become negative, meaning the entire result is positive, therefore they
I hope that melted my
That's
brain.
the first time I had to try it.
Oh.
I love it. Like, I got it right the first time.
Last
Like,
night.
I must have done something wrong, so let me just do the
I'll be honest, I didn't expect anybody to grab it. Yeah.
Yeah, it's just like, oh, I gotta check my work. I started doing that.
You're a good man.
Okay.
I'll see you.
Yeah.
No Mountain Dew. Damn. See, that's pretty done.
Hey, you don't need that.
Uh-huh. Game day.
I don't
I'll
care.
just turn this pretty game. I'll stop the other.
Erica.
Good morning, Douglas.
Good morning.
How you doing, sir?
Just got a weird email.
Why?
I forgot we had 2 games this week for East Coast Crew, so very weird email.
Why is that weird?
There's only one day. We'll have 3 that day. Only 1 week. We have 2, one today, 1 tomorrow.